going to want to estimate our electric cost in our factory, and we're going to consider, what do we got here? I think 8 different independent variables. And we're going to go through a process called backward stepwise regression to estimate a final model. If we want to look at each of these variables independently, we could see the explanatory power for our product A is 20%, product B explains 3%, product C 21%, machine hours 37%, and so on. So if we had to identify our best predicting variables, we would say fabrication hours, product A, not product A, but let's go with product C, fabrication hours, and machine hours, and really heat treatments up there as well. So we would sort of expect these variables right here, and I'm just going to highlight those in red to indicate that what going in seem to be our best explanatory variables. But again, these are independently. By itself, fabrication hour explains 52%. Machine hours explains 37%. Heat treatment hours explains 21%. Product C, 21%. And clearly all that adds up to more than 100%. So we will see the explanatory power of these variables will change as we go on. There's 2 different ways we can do a stepwise regression. One is forward stepwise, where we estimate a 1 variable model. And in that case, our best 1 variable model would have been the one with the highest explanatory power, fabrication hours. Then we would estimate a model using fabrication hours and heat treatment. We would run another one, fabrication hours and direct labor. Another one, fabrication hours and outside temperature. Another one, fabrication hours and machine hours. And we would run then 7 2-variable models. And we would pick the best of those 2 variable models and then add a 3rd variable to it and run 6 3-variable models, and then 5 4-variable models, and so on. It's a rather time-consuming process. Minitab or SPSS can run those automatically, but it's nothing we'd want to do manually. Instead, we're going to use backward stepwise, which is going to include first all of our independent variables, and then we're going to eliminate variables one at a time. So what do we want to do? Let's do our data analysis. Data analysis, and we're going to want to run a regression. We want to estimate what? We want to estimate our electricity cost using all of our independent variables. Again, I included labels, and that's very important. Where do I want to put my output? I'm going to put my output somewhere on this worksheet, right down here. And I would hit OK. Here's my regression output. First time when I look at this output, I want to pick the variable that has the least explanatory power. In other words, the smallest p-value. Negative p-values don't mean it's small, it just means there's a negative relationship, or negative t-stats rather. The least explanatory power is hours in heat treatment. So we're going to want to run our regression again, and this time we're going to want to eliminate the hours spent in heat treatment. Notice, first thing, hours in heat treatment, we thought explained 21% of our variability. We thought it was a decent variable. But in a model that includes these other variables, it's much like that high school SAT score. It doesn't add much explanatory power. So we're going to run our regression again after removing hours in heat treatment. So we're going to come up to our data set, and I would encourage you to make a copy of this before you do this. We're just going to delete that column. Now we can run our regression again. Data analysis, regression. We want to explain our electricity cost, our input range. Now instead of going all the way over to column J, it's only going over to column I. Where do I want to put my data? Output. Let's put it down below. Let's put it right here and hit OK. Let's change our formatting here so we can read them a little bit easier. And we want to, again, eliminate the value with the least explanatory power. Our p-value, and again, that was our probability of making a type 2 error. We've got 32%. Looks like product B. It has the smallest explanatory power. It has the lowest t-stat or highest what? P-value. So we're going to want to run our regression again now, and we're going to want to eliminate product B. So we'll come up here, delete product B, data analysis, regression, same dependent variable. Our independent variable range now, instead of going over to column I, only goes to column H. Where do I want to specify and put the output? Let's not overwrite the old output. Let's do another one. Let's put it right there at B86. Hit OK. And let's look at these coefficients. Again, let's just change the formatting slightly. P-values. Which one has the biggest p-value? Product C. Oh, nope, we're down here. What? Average outside temperature. Basically what we're saying is that there's what? A 28% chance that outside temperature coefficient really is 0. We have gotten that 2.599. It's our best estimate, but it's just by chance. So again, we're saying there's a 28% chance that the real value is 0. That just happens to be our set of data that gave us this 2.599. So let's go ahead and eliminate that. That's too big of a probability that there is really no relationship. So coming up to outside temperature, let's delete that from our data set. Run data analysis again. Regression. Our independent variables now only go over to column H. Output. Let's put our output down below. Again, let's change our formatting just to read them a little bit easier. P-values. The one with the highest p-value now is what? Product C. With all these other variables in the model, there's a 17, roughly 18% chance that product C really isn't significant. So in other words, if we wanted to have a 90% confidence interval, in other words, only a 10% chance of including a variable that shouldn't be here, we want to get rid of product C because there's a 17% chance that the real relationship is 0 and it's not 2.35. So let's run our backwards regression one more time. Get rid of product C, and notice again, product C was one of those variables we had picked early on to be included in a decent model. But in the presence of these others, it just doesn't seem to add a lot of explanatory power. Let's run data analysis one more time. Regression. Our independent variables now only go through column F. Where do we want to put our output? Let's put our output down here below. Again, change the formatting just so we can read things a little bit easier. P-values. Now if we look at our p-values, if we had a desire for only making a 10% confidence interval, in other words a 10% chance of including a variable when it really shouldn't be included, notice the p-values for all of these 4 remaining variables are all coming in at a significance value or a p-value of less than 10%. So our final model would include product A, machine hours, hours of fabrication, and direct labor hours. If we wanted a 5% or a 95% confidence interval or a 5% alpha, we would run this again and we would do what? Exclude machine hours. But if we've got a 10% confidence interval, we'll stop right here and we have a final model that includes these 4 variables. For your Excel homework, you're asked to go through a similar exercise. Basically different data, but similar exercise. One thing you're going to want to make sure you do at the bottom here, I give you values for all of our independent variables. You only want to include those independent variables that happen to be in your final model, whatever those happen to be.